Good afternoon, everyone. Someone has already joined. Okay. I think I should wait for some more time, 1 or 2 minutes, because people are still coming. So, okay, let's start the class. Hello, everyone. Today. Okay. Today I'm going to share. Yeah. So let's start our class today. I'm sharing my screen at first. If someone. Okay. Okay, I'm sharing my screen. Can anyone see my screen? Can anyone respond, please?
Yes, ma'am.
Okay, fine. So the course name of our class is Nuclear and Particle Physics, and this is, today I am going to talk about assignment 1 for week 1 session. Okay. So the course instructor is Professor Paulus, and I am Papia Panda from PMRF Nptel Teaching Assistant. And today I am going to say about 7 questions. Today I am going to talk about 7 questions, and 7 questions means there should be some questions at first, and after that the explanation of that question as well as the answer of that question. So if anyone have any doubt about any of the question, then please let me know at that time. So I think I should start by question number 1, and after that if anyone will come in between that, I will join them. Okay, so coming to the question number 1, the first question is like estimate the radius of the nucleus, which is calcium 2045, and it should be unit of Fermi up to 1 decimal place. So let me write something in that. Oh, sorry. Okay, so here the question is like the nucleus is calcium 2045. The nucleus is calcium 2045. So calcium 2045, what is the meaning of this notation? The notation means that we have Z equals to 20. Z means the number of proton is 20, and also the number of electron is also 20, and A is 45. A means mass number, which is nothing but neutron plus proton. So what will be the value of neutron? Neutron value will be 25. That means 45 minus 20. So the question is, what will be the value of the radius of that nucleus calcium 2045? The expression for this will be like the radius of the nucleus is given by the expression r equals to this one. This expression number 1 is the exact expression for any calculation of any of the nucleus's radius, which is r equals to r0 a to the power 1 by 3. So what is r0? R0 value is 1.3 into 10 to the power minus 15 meter. So here okay, so here the r0 is 1.3 into 10 to the power minus 15 meter, which is nothing but the average radius of a hydrogen atom with the atomic with mass number 1. So the r0 value is 1.3 into 10 to the power minus 15 meter, that is 1.3 Fermi, because we know that 1 Fermi equals to 10 to the power minus 15 meter. So r0 is 1.3 Fermi, and in this case A is given as 45, as I already told in the previous slide that A will be 45. So that means A is 45 for calcium 2040 and r0 is 1.3 Fermi. So by putting the above results, above values, we can have the radius of the calcium 2045 as 46 into 10 to the power minus 15 meter, which is nothing but 4.6 Fermi. So the correct answer will be 4.6 Fermi. So this is about the first question. So the first question is basically very simple, that we are going to use the simple expression r equals to r0 a to the power 1 by 3. So is there any
Hello.
question?
Yeah. I have a question here.
Yes.
What value we should take for R naught? Because some books take it as a 1.2, professor take it as a 1.25, and you have to take it as a 1.3, because there will be slight variations in every time.
Yes, like basically r0 is the average value for hydrogen atom, hydrogen atom nucleus. So it's a average value. You can take any value, like let's say whatever you have said here, that 1.2, 1.25 or 1.3. These three
Three,
value,
yeah.
yes, these three value are there, as you notice each and different books have different values. So we can take any one of them, because it's an average value. It's not that it is an exact value. So it's the average value. So we can take anything like 1.2, 1.25, 1.3. Basically it's in unit of Fermi, that means 10 to the power minus 15 meter, which is very small. So like 1.2 Fermi, 1.25 Fermi or 1.3 Fermi, that does not make any big difference. So
Okay.
you can take any one of them. Okay.
Okay. Yeah.
Yeah. So that means r equals to r0 a to the power 1 by 3, and by putting r0 as well as a value, we can have the value of r in our question. So this is up to the first question, and as in that first question it is saying that it should be in the unit of Fermi, that's why we have converted these all expressions in terms of Fermi. So that means 4.6 Fermi will be the correct answer. Okay, coming to the next question. The next question is, evaluate the binding energy of neon 1022. Use the So we have to evaluate the binding energy of neon to 1022, and here for calculating binding energy of neon, we have to use the expression for binding energy in terms of A and Z. And in the question also, the coefficients of different terms are given, like AV, AS, AC, A asymmetry and AP. These values are given here. So I will say each and every term, what term stands for what, and all the things I will say. But before that, I would like to say something about neon. 10, 22. So as I already told about that notation, for neon 10, 22, Z will be 10, A will be 22, and N will be 12, because 12 plus 10 equals to 22. So that means N and Z both are even number. Okay, so as well as A is also a even value. So that means any 10, 22 has A, N, Z, all are even. So what does this means, and why I am telling like that? Because the term AP, which is pairing term, it has a different value in different nucleus. I will tell what what does it mean a little bit later, but before that, okay, as just to remind that neon 1022 has N, Z and A all are even. Okay, so coming to the explanation of that expression question, in this question AV, AS, AC, A asymmetry and AP all are given, but what is the expression for binding energy? The expression for binding energy is given as equation number 2, as we can see here. EB is the binding energy, which has some terms. Some terms means the first term is AV into A. In equation number 2, the first term is AV into A, second term is AS into A to the power 2 by 3, and all the terms are here. So first term gives basically AV. AV is the volume term, volume term coefficient, and AV into A is the volume term. So why it is like that? Because we know that our volume is like R cube. So from the previous question, we have noted that R equals to R0 A to the power 1 by 3. So as a whole cube. So that means R0 cube and A will be there. So AV is basically a constant with R0, because R0 is itself a constant. So a constant with R0 cube and A will be there. So that means AV into A is there. So what does it means? It means that our binding energy depends upon the volume term, and the next term, the second term is AS A to the power 2 by 3. Why A to the power 2 by 3? Because AS A to the power 2 by 3, this term is called a surface term, and surface term is basically depends upon R square. So that means A to the power 1 by 3 whole square. That means A to the power 2 by 3. So let me erase something, otherwise. So that's why the surface term is A to the power 2 by 3, and the surface coefficient is known as AS. Now coming to the third term. The third term is AC Z into Z minus 1 divided by A to the power 1 by 3. This term is basically coming from the Coulombic term. So for Coulombic term, as we already know, the Coulombic nature or Coulombic expression will be like that, something divided by R. Like Q into Q divided by R. So R is basically nothing but A to the power, R is proportional to A to the power 1 by 3. So that's why in that AC Z into Z minus 1 divided by A to the power 3, A to the power 1 by 3, we have that expression. And the fourth term is A asymmetry, A minus 2Z whole square divided by A. Why it is like that? Because A minus 2Z, if I write this one here, it is not working. Just a minute. A minus 2Z is basically N minus Z, because N is A minus Z and minus Z, so that means A minus 2Z. So the fourth term basically describes about the asymmetric term, which comes as a asymmetric coefficient term and a minus 2z whole square divided by a. And the fourth one and the last term is basically a pairing term. I would like to say something more about the last term. In that last term, let me erase all the things and after that I will say. Okay. So what about that last term? The last term is basically AP. It has some values like it will be positive, it will be 0, or it will be negative. So when it will be positive, when it will be 0, and when it will be negative. When A is A, N, Z all are even, then AP has the value positive. When it will be 0, when A is odd, and when it will be negative, when A is even but N and Z are odd. Okay, so in our question we have taken any two 10, 22. So that means A equals to 22, Z equals to 10, and N equals to 12. So that means all the three terms A, N, Z all are even. So that's why we have taken AP equals to positive 34 MeV. So in like that the equation number 2 has constructed, and in that equation we have just going to put A equals to 22 and Z equals to 10 in our equation number 2. Then the answer will be like 187.33 MeV, and the correct answer obviously will be 180.33 MeV. So the equation number 2, in that equation number 2 the main variable is like Z and A. So by putting Z and A we can have the value of binding energy, but we have to consider that what will be the value of AP, the pairing coefficient, for our expression for our binding energy calculation. As it is given as a neon 1022, that means all the three terms are even. So that's why the equation number 2 has a positive value of AP, and we have calculated as with the value of positive of 34. You can see here that positive of 34 is there. So that means because obviously A, Z and N all are in even. So after calculating all the things in equation number 3, we can get the correct value is 187.33 MeV. So the correct answer for our question number 2 will be 187.33 MeV, which is the binding energy of neon 1022. So this is about the second question. Now coming to the third question. Third question is a little bit tricky, but not that much. Third question says about mass of proton and neutron are given like 938.27 MeV and 939.56 MeV respectively, and we have to calculate the binding energy of potassium, which is 1939, given its mass equal to this much U in units of atomic unit. So we have to calculate the binding energy of potassium here, where the given numbers are mass of proton and mass of neutron as well as mass of potassium itself, and we have to use the conversion formula that 1U equals to 931.5 MeV, and we have to give our answer in MeV up to 2 decimal place. This is the question for our question number 3. So just as the very similar of previous 2 questions, I can write like that. Potassium 1939 is basically gives us Z equals to 19, A equals to 39, and N will be 39 minus 19, which is 20. So here we can see that Z means proton number is 19 and neutron number is 20, and each and every proton and neutron has the mass of 938.27 MeV and 939.56 MeV respectively. So this is given in our question. Then what will be the answer for that question? The binding energy is nothing but the energy which binds our nucleus, and also the mass. It is given here that mass of potassium is 38.963706 U, but it is in a unit of U. So at first we have to convert that expression in terms of MeV. So for MeV, as it is given here that 1 U equals to 931.5 MeV, so basically we have to multiply this 38.963706 with 931.5 MeV to get the value of the mass of potassium in units of MeV. So the MeV unit, the MeV result will be 36294.69 MeV. And also, okay, now coming to the mass of proton and mass of neutron, as we can see that here for potassium the number of proton is 19 and number of neutron is 20, as I already told in the previous slide. So that means the binding energy is basically 19 into 938.27 plus 20 into 939.56. That means it in that bracket portion it gives the total mass of a neutron as well as proton, and the last term which is basically the mass of potassium. So that means the binding energy is the difference between that neutron and proton total mass and minus the mass of that nucleus. So the mass of the nucleus is 323.64 MeV, and it obviously in the range in the unit of MeV, because I have converted all the things, all the masses and all the things in MeV. So that's why the expression so that's why the correct answer will be 323.64 MeV. And in that question, as it is given that you have to give your answer up to 2 decimal place, so that's why I have just calculated only up to 2 decimal place, that means 323.64 MeV. So this is about the third question. Now coming to the fourth question. The fourth question gives a little bit long question and answer also. The question is the find the most stable isotope among the following. There are 4 nucleus is given here. One is S1635, S1636, S1637 and S1638. So these 4 isotopes are given and we have to calculate which one is the most stable isotope among these 4 isotopes, 4 nucleus states. So before going to the answer of that question, as we can see here, just like that previous one, all the things we can calculate that S1635, 1636, 1638 and all the things have all the isotopes has Z equals to 16 and A equals to 35, 36, 37, 38 respectively. So according to that we can say that what will be the value of N here. Like in that equation in that one, okay, just a minute. Yes, here's S1635, that means Z equals to 16, N will be 35 minus 16, which is obviously a odd number. Okay, but for 1636 Z is even, N is also even, and A is obviously a even number. And for this one 1635, A is odd, and for S1637 also A is odd, and for S1638 A is even. So just clarify all the 4 isotopes here. So basically what will be the most stable isotope among these 4? It can be understand by the calculation, by the value of the binding energy per nucleon. Because if any nucleus has a binding energy per nucleon very much greater, then it obviously have a stable isotope. So among these 4 isotopes we have to calculate which one is the most stable isotope by calculating the binding energy per nucleon among the 4 isotopes. If which one has the binding energy per nucleon is the most value, that means largest binding energy, this one will be the most stable isotopes among the following. So for that we have to calculate each and everyone's binding energy per nucleon. As I already written here, the isotope for which binding energy per nucleon is the largest will be the most stable isotope. And obviously the binding energy of any isotope will be written as EB equals to AV into A minus AS A to the power 2 by 3 minus AC into ZZ minus 1 divided by A to the power 1 by 3 minus A asymmetry A minus 2Z whole square by A plus AP A to the power minus 3 by 4. And also the coefficients are given in that way. So putting the values of AV, AS, AC, asymmetry and AP in that equation of EB, we can say that what will be the value of what is the binding energy for S1635. So for S1635, as I already mentioned there, that A is odd here, so that means AP will be 0, because when A will be 0, A will be odd, then only AP will be 0, and this one is even, and minus value will be when A is even but N and Z will be odd. Okay, so for the first one, that means 1635, A is odd, so that means AP will be 0. So just neglecting the last term of that expression of binding energy, we are calculating after putting all the values of AV, AS, AC and asymmetry as well as A and Z. We have the value of binding energy is 307.424 MeV, and I have mentioned here EB35 means the binding energy for S1635. So now come to the binding energy per nucleon. Binding energy per nucleon means here all A is 35, that means the number of nucleon is 35, so that means binding energy per nucleon will be the binding energy divided by 35. So after calculating this, we can have 307, what was the value, 307.425, yeah, 307.424 divided by 35, which is nothing but 8.78 MeV. So this is the value of binding energy per nucleon. And but binding energy per nucleon for S1636 will be something like that 318.05, because here in that case of S1636 we have to add this the last term AP A to the power minus 3 by 4, because S1636 has N, Z, A, all are even. I have already mentioned that we have A36 and both N and Z are even, so AP will be 34 MeV. It is not like that AP will be 0 in that case. AP will have the value positive 34 MeV for the case of S1636. And what will be the value of binding energy per nucleon? It will be 318.05 divided by 36, which is nothing but 8.83 MeV. And for the other two cases also we can write here 1637 as 37. You can see that 37 is basically a odd number, so that's why AP will be 0 here. And after calculating the binding energy calculation and also after dividing it with 37, we can have 8.73 MeV value for binding energy per nucleon of S1637. and for the next one also. For the next one 1638 is there. So as I already mentioned, 16 is the Z value, A is 38 and N will be 38 minus 16, so that means 22. So that means 38, 16, 22 all are even number. That's why AP will be 34 MeV. And after taking the binding energy per nucleon calculation, we can have the value of binding energy per nucleon is 8.727 MeV. So by comparing all the values here, the 8.72, 8.73, 8.83 and 8.78, we can have the most, largest value of the binding energy per nucleon for among that 4 isotopes is the one which is S1636. So that's why the binding energy per nucleon is the largest for S1636. That means the most stable isotope will be S1636. So that means our correct answer will be this one, S1636. This will be the most stable isotope among that four isotopes. So this is about the question number 4. Now coming to the question number 5. The question number 5 says that you have to calculate the the question is like binding energy of deuteron is 2.2 MeV. It is given here, and the frequency of the photon needed to dissociate the proton and neutron in deuteron is dash into 10 to the power 20 Hertz. So that means the question is basically what will be the value of frequency of the photon which needed to dissociate the proton and neutron in deuteron. So as I already know that in that deuteron is nothing but H12. So H12 means in that inside that nucleus there will be one neutron and one proton. So in that inside the nucleus one neutron and one proton will be there, and the question gives us that the binding energy of that deuteron is 2.2 MeV. It is given here already in that question. So we have to calculate what will be the frequency of the photon needed to dissociate the proton and neutron in the deuteron. So for dissociation of neutron and proton from the nucleus, we have to calculate what will the value of the frequency of the photon. So for that it's a very simple question, because we can assume that the frequency of the photon to dissociate the proton and neutron will be nu. So now the binding energy of the deuteron is basically 2.2 into 10 to the power 6 eV, because it is given already the 2.2 MeV. So the binding energy is basically the energy needed to dissociate P and N. P and N means proton and neutron. As in that deuteron there is nothing but only one proton and only one neutron, so that it is binding energy is equal to the energy needed to dissociate that proton and neutron. So that means EV equal to H into nu, and H is the Planck's constant and nu is the frequency frequency of that photon needed to dissociate the proton and neutron. So therefore just putting the value of EV in equation number 5, and equation also the H is given in equation, yes, this one is the H value 4.136 into so H is 4.136 into 10 to the power minus 15 electron volt into second. So after converting all the things in electron volt, we are just going to calculate nu, which is nothing but nu will be E divided by H. So E is 2.2 into 10 to the power 6, it will be in EV, and 4.136 into 10 to the power minus 15 EV into second. So that means the expression will be in second inverse, which is nothing but Hertz. So as the answer will be 5.3 into 10 to the power 20 Hertz, and in that question it was just asking that what will be the fraction here in that blank portion, that into 10 to the power 20 Hz. So we can say that the correct answer will be only 5.3. So this is about the fifth question. Now coming to the sixth question. So the sixth question is like, if the spin of a bound state of one neutron and one proton is measured to be 2 and it has even parity, then what are the possible values of relative orbital angular momentum between the neutron and proton in this bound state? So before going to the answer of that question, I would like to say something like spin. If I want to mention it as I, that means L plus S. What is L and what is S? L is orbital angular momentum, orbital angular momentum, and S is spin angular momentum. Okay, so here and also that I will be L plus S, but L plus S is like, it is not a simple addition, it is a vector addition. So I will say what is why I am saying that it is not only a simple addition, it is a vector addition. There is a little bit difference between simple addition and vector addition. Just forget about this right now. So in that question, basically it is given that I equals to 2, and one thing is also given, it is also given that even parity is there. So even parity means parity has a expression that minus 1 to the power L. So that means it is positive here. Even parity, that means it has a value positive. Okay, so if this condition is there, so that means obviously L should be like 0, 2, 4, 6, 8, something like that. I don't know right now that what will be the value of L, but I obviously assured that L will be 0 or 2 or 4 or 6 or 8 or something like that. It should not be like 1, 3, 5, because if minus 1 to the power 1 is there, so that means it will be minus 1, but obviously minus 1 is not a even number, so that's why minus 1 is not a positive number, so that's why it is not a even parity. So that means as our question gives us that it should be given as a even parity, that means L will have the value 0, 2, 4, 6, 8, something like that. Now coming to the value of L, what will be the value of L? Like one condition is there that L should be in between these values, but exactly what will be the value of L? Okay, so here as I already told that I equals to 2, and angular momentum is the sum of orbital angular momentum and spin angular momentum. Now here the bound state is like one neutron and one proton system. So one neutron and one proton, both have spin half. As I already know, these both are the Fermi particle, so that means this obeys the Fermi statistics. So and also both have the spin half. So what will be the value of S of that system? It will be half plus half minus half. Basically half minus half to half plus half, I can say like that. So that means 0 to 1 in steps of 1. So in that 0 to 1 there is nothing in steps of 1. So that means the value of S should be 0 and 1. So if the value of S is 0 or 1, so that means there are two options. One option is S equals to 0, and the second option is S equals to 1. So if S equals to 0, we already have I equals to 2. That means L obviously 2. Otherwise there will be no addition. So L can have two values, either L equals to 2 and L equals to 1. Why L equals to 1? Because in that second option, if S equals to 1, then L equals to 1, so that I equals to 2 will be there. So as the bound state has the even parity, and also as I already told that L can have 0, 2, 4, something like that. So that means L equals to 1 is forbidden in our system. So only the value of our orbital angular momentum will be L equals to 2, because if I write L equals to 2, then minus 1 to the power 2 will be a positive number, which will give the even parity of our system, bound system. And also the L equals to 2 and S equals to 0 will give us I equals to 2, which is obviously given in that question. So that means the right answer for that question will be the possible value of relative orbital angular momentum between the neutron and proton in this bound state will be obviously option number 3, which is 2. So this is the question number 6. And now coming to the question number 7. The question number 7 is a very only one number question, you can say that it's a true or false question. The question is like that: magnetic dipole measurements of deuterium reveal that it is always found to be in a state with relative angular momentum of neutron and proton equal to 0. Like, it's a statement and we have to say that the statement is true or false. So if it is true, then we have to click the A option, or if it is false, then we have to click the second option, B option. So basically, what does this mean of that question? The question means that the magnetic dipole moment of deuterium has the value equals to 0. Is it correct or is it not? Basically, the magnetic dipole moment of deuterium is not equals to 0. That means our question has the answer B, which is false here. This one will be the answer. But why this is like that? I have to say something about that. The magnetic dipole moment, which is basically mu has a relation like for deuterium, what is the configuration? The configuration is like that one proton will be there and one neutron will be there in the nucleus. So as the same of that previous question, that half will be there and half will be there. So that means S can have like a 0 or 1, something like that. And also, but S will be 1 for the deuterium case, as it's already proven. So that means S not equals to 0, and for S equals to 1, the two situation will be there. One will be L equals to 0 and L equals to 2. So L equals to 0 gives us J equals to 1, because it's a 1 and 0, 1. And the second, for the second configuration, 1 and 2 gives also a J equals to 1 value, as it is a vector sum, I already told you. So that means the expression for mu, that means the mu on magnetic deuterium, for deuterium the magnetic moment is mu has the expression like that. And for the first case, the value of mu will be 0.879, and for the second case, the mu has the value 0.310, and the measured value of the deuterium magnetic dipole moment is 0.857 mu n. Mu n is basically nothing but the Bohr magneton. It is a unit of magnetic dipole moment. And so that means basically the main thing for that is the deuterium magnetic dipole moment has non-zero value for deuterium, and also its angular momentum has a mixed state of L equals to 0 and L equals to 2. So that means correct answer will be B. That means we can say that the magnetic dipole moment measurements of deuterium is not equals to 0. That means our whatever it is given in that statement in that question number 7 is obviously false 1. So this is up to the seven question, and if anyone have some doubt on these questions, can you please tell? Like I have explained all the questions term by term, and basically the all the questions have a very simple expression that what is basically binding energy, what is the expression for binding energy coming from the semi empirical mass formula. And oh, I forget to tell what is semi empirical mass formula. This is the semi empirical mass formula. This expression for binding energy is known as the semi empirical mass formula, and this expression this EB expression comes from the liquid drop model. There are so many models. Liquid drop model. And why it is calling a semi empirical mass formula? Because semi empirical means the some portion can be calculated from the theory part, and some portion can be calculated from the experimental part. So EB is basically here the experimental part is coming from that AV, AS, AC, A asymmetry and AP. These coefficients values are coming from the experiment, so that means that's why it is calling as semi empirical. Semi empirical means theory is obviously there, and the empirical part, that means experimental parts, are coming from that AV, AS, AC, A asymmetry and AP coefficient. So that's why it is calling as semi empirical mass formula.
Hello, ma'am.
Yes.
Hello. Ma'am, what is the physical significance of asymmetric?
Okay, asymmetric. Basically the binding energy is what? Binding energy is the energy of that neutron and proton, like whatever it is inside the nucleus, the energy which binds these nucleons. So the asymmetry is like what terms are depend on the binding energy in that expression. The volume term is there, surface term is there. Volume term is like that if our volume term increase, then like that means that if our nucleus size increases, then obviously the binding energy will be increased. So that's why in between, in front of that AVA, a plus sign is there, like there is nothing, no sign, that means it's a positive sign. So and also for the surface term, Coulombic term, asymmetric term, these terms are basically responsible for decreasing the binding energy. So what is surface term? As I already is surface term means that surface the binding, the energy coming due to the surface contribution of that neutron and proton configuration. And for Coulombic term, as I already know that proton is a charged particle and neutron is a neutral particle. So there is no Coulombic term for neutron, but there is a Coulombic term for proton. So that's why the proton there will be a repulsive term, so that's why the binding energy will be decreased, and so that the minus sign will be there inside that Coulombic term. But what is asymmetric term? Asymmetric terms is like that, it is also a minus term. I mean, in front of that asymmetric term there is a minus sign. That means this also decrease our binding energy of our calculation. So this basically signifies that the asymmetry between the number of neutron and proton. Like if in any theory like oxygen 8-16, let's think that 8-16, 8 has the Z value is 8, so that means the proton number is 8, and a neutron number what will be? Neutron number will be also 8. So if neutron number is same as proton number, then what will be there is a symmetry between neutron and proton number. So that for that type of expressions, for that type of nucleus like oxygen 08, A asymmetry into A minus 2Z whole square divided by A, this whole term will be 0, because as I already know that 16 minus 2 into 8 will be 0. That means 16 minus 16 will be 0. So asymmetry is basically coming from the asymmetry between neutron and proton number. If in that nucleus neutron and proton number is different, that only then we can have that asymmetry term. Okay, so asymmetry term is basically a decreasing term for binding energy calculation, that's why it is a minus sign, and asymmetry comes from that neutron and proton number. Do you got the point?
Yes, ma'am. Thank you, ma'am.
Okay, so any other question? And
Ma'am,
this, oh yeah,
go to
fine.
the go to the last slide.
Yes.
Could you please explain again this in magnetic moment and whatever you speak here?
Okay, so magnetic moment, the question was here, the question was that the magnetic dipole measurement, that means the magnetic dipole moment of deuterium reveal that it is always found to be a state with relative angular momentum of neutron and proton equals to 0. So is it calculated or not? Okay, so the magnetic moment measurement of deuterium obviously says that our relative angular momentum of neutron and proton is equal to 0. Relative angular momentum of neutron and proton means what? What is that? Okay, relative angular momentum of neutron and proton is basically L. So the question says that L equals to 0 or not. Okay, so coming to the expression of that magnetic moment, the magnetic moment has mu this one and mu, where is that, yes, mu this one. So mu has two expressions in two different configurations. The first configuration is L equals to 0, what they are talking about, that expression. If L equals to 0 and S equals to 1, then mu has the value 0.679. But if the another condition is satisfied, then another configuration is there, that means L equals to 2 and S equals to 1, then also J equals to 1. So from that configuration we can have the mu as 0.310. These two are the theoretical calculation, but our experimental measurement shows that the measured value of the deuterium magnetic moment is 0.857 mu n. So it is not like that our mu value only comes from that expression, because it can be possible that our magnetic moment also comes from this expression also, that means L equals to 2 and S equals to 1, so that we can have the resultant magnetic moment as 0.857 mu n. And also it is, I have written here that its angular momentum has a mixture of two states, that means L equals to 0 and L equals to 2. It is not like that only L equals to 0 has the 100% contribution to the magnetic moment, that means only this configuration. The second configuration is also possible for deuterium, so that's why L equals to 0 has 96% contribution for magnetic moment, magnetic dipole moment calculation, and the L equals to 2 has 4% contribution to mu. So that means our question which says that only L equals to 0 is the actual one for our deuterium state is not true. That's why our statement is false here.
Okay, okay, I got it.
So is there any other question? Oh. Basically, the first assignment is a very simple and basic about the nuclear and particle physics. So there is nothing more than that.
Yeah, ma'am. You can explain.
Yes.
Explain what you
Which one?
say
Sorry.
about nuclear and body.
Sorry, I can't hear you. Hello. Hello. Rakesh, I think. Are you saying something?
No, ma'am. Sorry, I have doubt. I have doubt, and this is clear.
So these are the total 7 questions here, and in that next Sunday there will be assignment 2 explanation. And so if there is no other question, then I think we should stop the meeting. Thank you everyone. Thank you. Bye.
Thank you, ma'am.
Thank you, ma'am.
Bye. Thank you. Thank you. Bye.